So, in last class we have introduced a temporal logic called CTL, computational tree logic. So, what happens, we have seen what is the syntax of CTL and we have discussed how to define the semantics of those particular CTL. Okay, so, what happens in syntax, we have seen that if P is a atomic proposition or set of atomic proposition, then all atomic proposition will be treated as your CTL formulas along with the truth values true and false. And we have already seen that if we are having your logical connectives like your AND or implication, with all those connectives we can again form CTL formula provided phi is a CTL formula. On the other hand, we are having 4 temporal operators. Basically, we have discussed about 4 temporal operators: next state, future state, globally and until. So, with this particular 4 temporal operators, we can form CTL formula in conjunction with your path quantifier A and E. So, we are going to get these particular 8 different forms of your CTL formula: A x phi, E x phi, A f phi, E f phi, A g phi, E g phi, A phi until psi and E phi until psi. Okay. Now, what will happen in last class, we have seen how to define the semantics of those particular logical connectives. Today, we are going to discuss about the semantics of those particular temporal operators along with your path quantifier A and E. And already I have mentioned that in CTL, we are going to deal with state formula, that means temporal operator preceded by your path quantifier, then it becomes a state formula. We are going to define the truth values of temporal formulas with respect to state of a model. Now, how we are going to define the semantics? Already I have mentioned that to define a semantics, we need a model, we call it CTL model or temporal structure or Kripke structure, because it is having 3 components: set of states, a transition relation and a labeling function. Already I have mentioned what is labeling function. It is basically related to your atomic proposition which are true in that particular state, and we are going to label those particular state with the help of those particular atomic proposition. Now, we are going to see how we are going to define the semantics of our temporal operator. Now, first we are going to consider A x phi. This is your in all path in next state phi holds, and we are going to define it in a state in a model M state S. We are going to say that M S models A x phi if for all S 1 such that we are having a transition from S 1 to S 1, we have M S 1 models phi. So, you just see that we are going to consider one particular state S. We are going to look for all next state S 1 and such that this one in S 1 phi holds. So, in next state operator what will happen? We are going to see in next state whether something holds or not. If it holds, then we are saying that A x phi holds in this state. So, A x phi is satisfied at S if all next state of S phi is satisfied. So, just look into this particular model. Said we are going to look into this particular model, and these are the labeling functions. Say L S 0 is P, that means we are having a set of atomic proposition P where I am having P, Q, R. These are the 3 atomic propositions. So, we are having that labeling function. So, it stated in S 0 P is true, in S 1 P and Q is true, in S 2 Q is true and S 3 Q is true. Now, we are going to look for formula A x q. So, what does it mean? In all path in next state q holds or not. So, we are going to look into this particular state S 0. We will see come to your S 1, this is a next state, yes, q is true at that particular state because it is labeled with q. If you come to S 2, again you will find that q is also true over there. Similarly, in S 3 q is also true. So, we can say that in S 0 A x q is true. So, we say that M S 0 models A x q. So, this is the way that we are going to define the semantics of our formula A x phi. So, the semantics or meaning is defined with respect to a model. Now, the next operator is your E x phi, that means there exists a path in next state phi holds. So, it is similar to your previous one, but here we are going to concern about any path, not all paths. So, if for some state S 1 such that there is a transition from S to S1 when we have M S1 model phi. That means, we are going to get at least one transition S to S1. That means, S1 is the next state of S, and if we find that in S1 phi holds, then we say that MS models EX phi. So, that is why we say that EX phi is satisfied at S if in some next state of S phi is satisfied. So, similarly, we are going to look into this particular model M. We are having this same labeling function LS0, LS1, LS2 and LS3, and atomic proportion are PQ, only 2 atomic proportion we are having PQ. So, here we will say that from S0 we are having a transition to S1 where Q holds, again S2, again S3, on all the places Q holds, but here P holds in your S1. So, we are going to look for the formula EXP, whether there exists a part in next that P holds. If by looking into the transition from S0, we will see that there is a state called S1 where this particular formula P holds. So, we said that in your state this particular S0 EXP holds. So, we write it that in model M state S0 EXP holds. That means, EXP is true in this particular state S0. So, this is about the behavior of our next state. So, we are having two operator in temporal logic, one is your AX phi and second one is your EX phi. Now, next formula that we are going to look into our logic is your AG phi. G is a global operator and AG phi, it says that in all part globally phi holds or not. So, we said that if it is true in a particular state, we said that in model M state as AG phi holds. So, when we say that AG phi holds, if for all paths that we are going to consider all paths like that, we are having a transition from S0, S1 to S2, S2 to S3 and like that we are having a sequence of states where we are going to say that S equal to S1. That means, we are concerned about this particular state S, and we say that in all paths that starting state S0 is equal to your S and all Si along the path. And now, we are going to consider all Si, all other states along the path such that M in this model M Si model phi, that means, phi holds in this state Si, and what is this Si? Si is the all states along the path. That means, what it says that AG phi will be true in a state provided in all states along all the paths that phi holds. So, just say that AG phi is satisfied at S if all state of all paths from S satisfied phi. Now, I can come to this particular model M, just say that this is our model M. We are having 4 states S0, S1, S2 and S3 along with this labeling function where we are having that atomic proposition P and Q. Now, we are concerned about this particular formula A, G, Q, and we are going to look into state S0. Now, that means, when we concentrate this particular state S0, we will see the paths. Say it is having 3 different transitions. So, we are going to get 3 different paths starting from this S0. One will go something like that from S0 to S1, then S1, S1 like that. Second one will go from S0 to S2, then from S2 it will go to S1, then it will remain in S1 like that. And another part we are having, it will go from S0, it will go to your S3, from S3 it will go to S2, and from S2 it will go to S1, and like that it will remain in S1. Now, these are the 3 possible execution rates that we are going to get in this model. Now, we are going to look for all such type of part S1, S2, S3 like that, where S equal to S1. Now, my S is your S0. Now, from here we are going to see all the possible state, and we will find that all those state S0 and S1 that Q is true, it is labeled with Q. When we come by this particular part S0, S2, S1, 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 it is having a self loop. So, it is going to from S1 to S1. In all the steps, we are going to get that Q is true over here. And in third part, again we are going to get S0, S3, S2, S1, S1, S1 like that. And in all the steps, we are going to get that q is true. That means, all possible state in all paths we will see that, or we have seen that phi is true or q is true in this example. So, we can say that A g q is true in this particular state S 0. So, we say that in model M in state S 0 A g q holds. So, this is the way we are going to look for the meaning of your A g phi. So, next formula that we are going to get is your E g phi. So, it is again the global operator, but we are having the path quantifier as your E. That means, we are concerned about any path, we are not going to look for all the paths. So, that is why we say that in model M instead as it models E g phi. That means, we say that E g phi holds if there is a path. Now, we are going to look for any path such that it is going from state S 1 to S 2, S 2 to S 3 like that, where S equal to S 1. That means, the starting state of the path is the state that we are looking for, and all S I along the path that phi is true. So, M S I models phi, where S I is your all states along that path. So, that means, if we are going to get a path where in all states phi is hold, then we say that E g phi holds in the starting state of this particular path, that means S. So, we say that E g phi is satisfied as S if all states of at least one path from S satisfied phi. Now, again just look into this particular model M. Okay. We are having this particular labeling function L S 0, L S 1, L S 2 and L S 3 as P Q, P Q, Q 1, Q. Now, we are going to look for this particular E g P at state S 0. That means, there exists a path globally P holds. Now, again like previous case, we are going to get this 3 different path S 0 to S 1, S 1 to S 1 and like that. Again S 0 to Q, S 0 to S 2, S 2 to S 1, then it will remain in S 1. Again S 0 to S 3, S 3 to S 2 and S 2 to S 1 and it remains in Y. Now, we are going to look for E g P. Now, when we start from S 0, we are getting path to your S 1. In S 1, we have seen that P is true. That means, when we are going from S 0, it is your P is true. Then we are coming to S 1, again P is true, then it will remain in S 1 like that. All the path, if you see here in this execution trace from S 0 to S 1, S 2 to S 1 to S 1, S 1 to S 1, everywhere that P is true. But if you look into this second part S 0 to S 2 to S 1, we will find that state S 2 where Q is not true. So, that means, in this particular part globally P is not true. Similarly, if we go for the path S 0, S 3, S 2, S 1, then in state S 3 and S 2 that P is not true. That means, in this two path P is not true globally, but at least we have got one path S 0 to S 1 from S 1 to S 1, where in all the state P is true. That means, we can say that in this particular state S 0 that formula E g P is true. So, we said that in model M state S 0 that E g P holds. So, that says that M S 0 models E g P. So, we are getting at least one part where P is true globally, and that is why we said that E g P is true in state S 0. Okay. So, this is basically globally operator. That means, in all state it must be true. Now, the next temporal operator is your F, future. Already you have seen that in some future state or eventually something must hold. So, we say that in model M as it models A f phi or A f phi holds in that particular state as provided for all paths. Now, since we are going to have this particular path quantifier A, so we are going to look for all such type of path going from S 1 to S 2, S 2 to S 3 like that, where S equal to S 1. That means, the starting state of all those paths is the states of our concern that we are looking for this particular state S, and for at least one S I along the path. Now, we are saying that at least one S I along the path M S I models phi. So, you just see that we are going to look for all paths. In all paths, we are saying that eventually phi must true. That means, we are going to look for some state whether phi holds over there or not. In that case, if this is going to happen in all paths, then we are going to say that A f phi holds in this particular state S. Now, again look for this particular model M. Okay, we are having 4 state S 0, S 1, S 2 and S 3, and this is the labeling function of this particular 4 state S 0, S 1, S 2 and S 3. Now, we are concerned about this particular formula A f q in state S 0. Now, again we are going to get the part S 0 to S 1, S 1 it will remain in S 1 because we are having a self loop. Similarly, we are going to have S 0 to S 2 and we are having a transition from S 2 to S 1, then S 1 like that. Again in the another part from S 0, this is going from S 0 to S 3, from S 3 we are having a transition to S 2, from S 2 S 1 like that. So, these are the 3 possible paths. Now, we are going to look for E A f q, that means whether we are going to get a fusor state where q holds. Obviously, you see that when I go by this particular path, we are getting a state S 1 where q is true. When I will go by this particular path, again we will find that in S 2 q is true. Again if I follow this particular path, we will find that again q is true in S 3. That means, in all 3 paths in some fusor state, we are going to get q as true. So, you just see that here it happens to be in the very next state, but it may happen that in next state it is not true, but in some fusor state it is true. Then we are going to say that in all path in fusor q holds. So, we say that M S 0 models A f q. So, we are going to look for this particular formula q, which is true in some fusor state along all the paths. Okay. Now, next formula is again with this fusor operator, but with this path quantifier E. That means, there exists a path in fusor phi holds. So, again it is similar to this thing, we are going to concern about any one path. We are not going to look for all the path, but if it is true in any one path, then we are going to say that E f phi is true. So, again we will say that we are going to look any one path going from S 1 to S 2, S 2 to S 3, where S equal to S 1, that means starting state of the path is equal or is the state of our concern S, and for at least one S I along that path M S I model phi. That means, phi holds in some state S I along that particular path. In that particular case, we are going to say that E f phi holds in that particular state. Again look for this particular model M, and my state of concern is your S 0 and the formula is your E f p. Here exists a path in fusor p holds, and this is the labeling function that we have q, p q in your state S 1, in S 2 q is true and S 3 q is true. Now, you just see that we are having those particular path S 0 to S 1 to S 1 like that, we are having an infinite sequence. Second part is from S 0 to S 2, from there is a transition from S 2 like that. I have slightly changed the model. Now, again third part we are going to get S 0 to S 3, from S 3 we are having a transition to S 2, then we are having a transition from S 2 to S 2 like that. These are the 3 possible paths that we are going to get from this particular state S 0. Now, if you look these 2 paths from S 0 to S 2 and it will remain in S 2. So, we are going to get the sequence S 0, S 2 from S 2 to S 2 like that. In none of the fusor state P is true. That means, in this particular part we are not going to say that P will be true in fusor. Similarly, the path S 0, S 3, S 2, if you consider this particular part, again we will see that we are not going to get any fusor state where P is true. But if you follow this particular path S 0 to S 1 to S 1 like that, then that S 1 is marked with your P, that means P is true over here. That means, we are going to get at least one fusor state where P is true. So, due to this particular part, we say that in S 0 E f p is true. So, this is the way that we are going to define the truth values of E f p. Now, the next operator is your until, because already I have mentioned that the 3 operator that we have next state, fusor and global, These are unary operator, it works with one particular formula, but until is a binary operator. So, it works with two temporal formulas. So, we are going to say that phi 1 until phi 2, and this until operator must be preceded by part quantifier either A or E in case of your CTL. So, that is why we are going to look into this particular formula A phi 1 until phi 2. That means, in all part phi 1 remains true until phi 2 becomes true. So, we say that this formula holds in a state S of model M, provided for all such type of paths that we are going to look having a transition from S1 to S2, S2 to S3, where this particular starting state of the path S1 is equal to the state that we are looking for, and we say that phi 1 until phi 2 is satisfied if there is some SI along the path. Okay, now, we are going to look for those particular paths such that M of SI models phi 2. That means, we are going to get some state SI where phi 2 is true, and for each j is less than I. So, we are going to get one particular state SI where phi 2 is true. Now, we look for all other state SI where Sj where j is less than I. We must have M as j models phi 1. That means, phi 1 must be true all those particular state Sj. Now, just consider this particular model M over here, and we are looking for this particular formula A P until Q in state S0. Now, in this particular case, you just see that if I am having this now execution trace something like that, from S0 it is coming to S1, from S1 we are coming to S4. So, we are having an execution trace S0 to S1, S1 to S4, like that it is an infinite path. Second one, we are looking for this particular part S0 is having a transition to S2, S2 is having a transition to S5. In S5, we are having a self loop. So, we are having a transition to S5 like that. Again, we are having another part from S0, this is your S0 is going to your S3, and from S3 we are having a transition to S6, and it is having a part from S. Now, if you look into this thing, we are concerned about A, P until Q. That means, we have to look for all these three parts, and we are going to look for one future state where Q is true. Now, in this particular first part, we are going to say that Q is true in your S4, and in that particular case, if Q is true in some state, then we have to look for all preceding state of those particular state in that particular part, and we have to see whether P holds over there or not. So, we will find that P is true in S1 and P is true in your S0. That means, in this particular part P until Q is true. With the similar reasoning, you can look for the other two parts also S0 to S2, S2 to S5, you will find that P remains true until Q becomes true in this particular part. And similarly, in third part also you will find that P remains true until Q becomes true. So, we have seen in all these three parts P until Q is true. That means, we can say that in that these three parts are coming out from this particular state S0. So, we can say that in state S0 of model M, A P until Q is true. Okay. So, this is the way that we are going to look for the two values of the formula A phi 1 until phi 2 or A P until Q. So, similarly, now we are going to look for the last formula where it is with until operator at the path quantifier E. That means, we are concerned about any path, there exists a path. So, that phi 1 until phi 2 holds from this particular in a particular state S. Again, in this particular case, what will happen? We are going to look for at least one path such that it is going from S1 to S2, from S2 to S3, where S equal to S1, that means, the starting state of this particular path is our concerned state S, such that phi 1 until phi 2 is satisfied in this particular. What does it mean? That means, we are going to get a state S I where phi 2 is true, and all the preceding state in the path from this S I phi 1 must be true. That means, for each j is less than I, M as j models phi 1. So, this is similar to your A phi 1 until phi 2, but here we are concerned about one particular part, any particular part, that is why I said that there exists a part. So, with E quantifier. So, I can just look for this particular model M, we are having this particular label, this is with respect to your leveling function. So, we are going to look for the formula E P until Q in state S 0. Again, similar to our previous case, we are going to get 3 part S 0 to S 1 to your S 2, then S 0 to, sorry, this is your S 4, then S 2, then it is going to S 5 and it remain in S 5, then third pass is your S 0 to S 3, then from S 3 to S 6. Now, we are going to look for P until Q. So, if you look into this particular part, at least since it is an infinite sequence, but we are not getting any states where Q is true. Similarly, if we look for this particular part, so this is again going from S 5 to S 5. So, there is no possibility that we are going to get any state where Q is true. So, here we may get somewhere Q is true, but in this particular state, previous state, that P is not true, at least here P is not true. So, if you look into this particular part, you will find that we are getting S 4 where Q is true and it is having two preceding state S 0 and S 1. So, in these two preceding state P is true. So, that means, we are getting this particular part where P until Q is true, but in other two part P until Q is not true. Here it is obvious that P until Q is not true, because we are not getting any state where Q will be true, but since in this particular part we are showing an infinite sequence, that means, in far behind we may get a state where Q is true, but at least we will find this particular state where P is not true. Secondly, S 6 P is not true, that means, P will not remain true until Q becomes true. So, it is also overlooked that in this particular part we do not, it is not going to satisfy E P until Q. So, that in this particular case at least we have got one path. So, from that we can conclude that in this particular state S 0 P E P until Q is true. Okay. So, this is the way that we are going to define the meaning of our CTL formula. Now, till now what we have discussed, we have seen one particular temporal logic which is known as your CTL, computational tree logic. Generally, the truth values of temporal logic is defined over a model which is having transition and states, but in case of CTL, basically we have already said that this particular model can be unfolded to a tree and the semantics is basically defined on a tree. So, we are saying that this is your computational tree logic, and we have seen that 4 temporal operator that we have along with 2 part quantifier A and E, we are going to get 8 different possible temporal operator in case of CTL, and all temporal operator must be preceded by a part quantifier, and due to that reasons the formulas of CTL becomes our state formula. So, we define the truth values of a formula with respect to a state, and this is due to the presence of this particular part quantifier. So, now just see that what will happen, just I am showing here one diagram that we are looking for some formulas showing pictorially. So, we are concerned about this particular state as 0, we are having that atomic proposition Q, Q is an atomic proposition. Now, in the first diagram tree, we have looked for there exists a part in future Q holds. Wherever Q is true, just we have colored it with yellow. So, we will find at least one part where in future Q is true. In second one, I have said that A, F, G, sorry, this is Q, G. So, in this particular case, we will find that whether in all part in future it is true or not. So, we are looking for this particular part, it is starting from at least we are getting one state where it is true, and other two part we are having this way. So, in future we are getting this particular is true. So, we can say that AFG is true. Third is there exists a part whether globally something whole or not. So, this is the part where everything is marked with yellow, that means this property is true in all this particular state of this particular part. So, we can say that EG is true. And fourth one is your AG all part globally, that means this particular formula is true all the states, you just say that. If it is marked like that, then we can simply say that AG is true over here, because in all part globally something is true, that particular G is true. So, that is why it is marked like that. So, by looking into this particular tree structure, very well you can see whether a particular formula is true in a particular state or not. Here we are going to look for this particular state as 0 starting state of this tree. So, like that we can see whether a particular formula is true in a particular model or not. Now, after defining the syntax and semantics of CTL formulas, now we will see some example to make it more clear, before proceeding further, because we will be knowing this. Now, just see that consider this particular model M. So, it is a model. What is model is having three components basically. First one is set of states, second one is the transition relation, and third one is your labeling function. So, in this particular model L, say S is a set of states. So, we are having four particular states S0, S1, S2 and S3. And this transition relation, how many transition relation we have? 1, 2, 3, 4, 5, 6. So, total 6 transition relation we are having. So, first one is having a transition from S0 to S1, then S1 to S2, S1 to S3, then S2 to S3, from S3 to S2, and we are having a self loop S3 to S3. And if you see that we have having one more condition where we said that the transition relation must be complete. What does it mean? It says that every state must have a successor state. If you look into this particular model, you will find that all those particular 4 states are having a successor state, because from all the states we are having at least one outgoing edges. And this is the labeling function. Now, what will happen in this model? We are having the set of atomic proposition V as your P, Q and R. These are the state of atomic, these are the atomic proposition that we have. Now, the labeling function says that L of S0 P. What does it mean? That means that atomic proposition P is true in S0, and indirectly it means that atomic proposition Q and R are false in this particular state S0. Similarly, in state S1, the labeling function says that P and Q, that means the atomic proposition P and Q is true in your S1. Labeling function S2 says that R, that means it says that the R is true in this particular state S2, and labeling function of S3 says Q and R, that means the atomic proposition Q and R is true in S3, but atomic proposition P is false over here. If it is false, we are not directly marking it, but indirectly it says that Q is false. So, now we are concerned about this particular model, and these are the 3 components. Now, we will see some examples over here with respect to this model. Now, the first question I said that find the states where the formula A F R holds, that means in all part in future R holds. Now, we have to see it is a state formula. Now, we are going to look for the state S0, and just say that this is my model M. So, in S0, if I go for S0, it is having this particular part, only one part is elementing, and we are getting that S1 going from S0 to S1. Then from S1, I am having 2 possibilities, either I am going to S2 and S3. Now, if these are the, and again from S2, it is going to S3, and from S3 again it is coming back to S2 like that, and from S3 it remain in your S3, or it may have another one also, it may go to S2 like that. But now you just see that in all part in future whether R holds or not. So, if you see look for all those particular parts, we will find that in one future state this S2 R holds and we are going to get one future state R holds. That means, you can say that in this model M S0 that in all part and future R holds. Now, similarly, you look for the state S1. If you look into this particular state S1, then you will find that it is having two parts and in future part in future state R is true. So, in S3 R is true and S2 also R is true. So, in all possible part in future we are going to state where R is true. So, we can say that in this model M S1 AF R is true. Similarly, when I come to your S2, then we will find that from S2 it is going to S3 where R is true, coming back to S2 and again going to S3. That means, all part we are going to get state in future R is true. So, again you can say that in your M S2 it models A F R. Now, when we come back to this particular state S3, so basically what will happen from S3 we are having a transition to S3 like that, or we can have that from S3 we are going to S2, coming back to S3, again going to S2 like that. So, we will say that in all those particular examples in future state R is true. So, we will say that in model M in S2 it also models A F R in all part in future R is true. So, now individually we have gone to each and every state and we have found that this formula A F R is true in all those particular 4 states. So, this is the way that we have to look into it, because the CTL formula is a state formula, the truth values of CTL formula is defined with respect to a state only. Okay. Now, this is the same model I am having over here, and now we are going to see the formula, find the states where the formula AG AF R is true or not. Okay. What does it means? In all part in future R holds, and it says that in all part globally whether this particular formula holds or not. So, now what we can say that R is an atomic proposition. So, we will say that R is a CTL formula. So, we know the truth values of R in each and every state. This is with respect to your labeling function. Then F is a temporal operator. So, F for it says that in future R holds or not, and A says that whether in all part in future R holds. So, this is AFR is also a CTL formula. So, we can say that this is your phi is a CTL formula. So, if phi is a CTL formula, then we will find that AG phi is also a CTL formula. So, that means AG AFR is a CTL formula. Now, we have to check whether this CTL formula is true in all states or not, or whether it is true in some states or all states in this particular case or not. So, now basically just say that when I am coming to that state S0, now we will see that from S0 whether it holds in all possible states in all possible direction or not. Now, just let us go back to my previous example. So, in previous example what we have seen that this AFR is true in all those particular 4 states we have seen over here. Now, what does it mean? Since AFR is true in all states, that means I can label those particular states with this particular formula AFR. So, now you can say that in state S0 AFR is true, in state S1 AFR is true, in state S2 AFR is true, in state S3 AFR is true. Now, it says that in all part globally AFR is true. Now, from S0 if you go in all possible direction you will find that AFR is true. So, we can say that in S0 in all part globally AFR is true. So, with similar logic what we can say that when we start from S1 then we will look for all possible part, all possible combination, and wherever I will go I will find that AFR is true everywhere. So, we can say that AG AFR is true in S1 also. With similar logic, you can say that it is true in S2 as well as it is true in state S3 also. That means, in all those particular 4 states of this particular model, M, A, G, A, F, R is true. So, when we are going to look for the truth values of a particular CTL formula, first of all we have to know the truth values of its sub formula. So, basically here if I consider this particular formula A, G, A, F, R, it is having 2 sub formulas. One is R, we must know the truth values of R in all states. Then another sub formula we are having A, F, R. Before going to A, G, A, F, R, we must know the truth values of A, F, R in each and every state. Then only we can look for the truth values of the given formula A, G, A, F, R. So, after analyzing this particular model, we have found that A, G, A, F, R is true in all those particular 4 steps. Now, this is simple one that I am again saying. Now, we are going to look for A, F naught of P. So, this is similar to our A, F, R only, just we are saying that it is naught of P. Now, how I am going to look into it? Say P is a atomic proposition. So, P is a CTL formula, because its atomic proposition is a CTL formula. Now, if phi is a CTL formula, then naught of phi will also be a CTL formula. So, I can say that naught of P is also a CTL formula. Okay. Now, if we are having any phi as a CTL formula, then we will say that A f phi is also a CTL formula. So, we will get that A f naught of P is also a CTL formula. Now, what about this particular naught of P? We are going to get the truth values of naught of P from our labeling function only. If it is not labeled with a particular atomic proposition, we will say that this particular atomic proposition is false in that particular state. Now, you just see that in your S 0 P is true. So, P remains true over here. In S 1 P and Q is true, that means P is true over here. In S 2 it is labeled with R. So, what does it mean? It says that Q and R is not true over here. So, we can say that naught of P is true over here. Similarly, in S 3 Q and R is true, it is labeled with Q and R. So, it is not labeled with Q. So, we are going to say that naught of P is true over here. Now, you just see that already I have analyzed this particular formula. In all part in future R is true or not. When we have analyzed this particular formula, we have found that in all those particular states A f R is true, because in future we are going to get one state when R is true. So, this is the same behavior we are going to get. Say in S 2 R is true, similarly naught of P is also true. In S 3 R is true, here also naught of P is true. So, the behavior of this model is same with respect to your the atomic proposition R and naught of P. Since A f R is true in all the 4 states of this particular model, similarly we can conclude that naught of A f naught of P is also true in all those particular 4 states of this particular model. So, this is the way that we have to see whether some CTL formula is true in some models or not. Now, just look for this particular model again, that this is the model M, and we are concerned about this particular formula A, P until R. P remains true until R becomes true. So, again we have to see all the states. So, from S 0 what will happen? It will go to S 1, say in S 0 P is true, S 0 P is true, then S 1 P is true, then we are going to get S 2 where R is true. This is one execution path. Similarly, another part we are going to get S 0, S 1 and S 3. So, again in S 0 P is true, S 1 P is true and S 3 R is true. So, we are getting some state in future where R is true, and in all the preceding state of this particular part, all those particular part P is true. So, we can say that in S 0 that A P until R is true. Similarly, if I look into S 1, it is simpler than the previous one, because from S 1 we are getting 2 state S 2 and S 3 where your R is true and the preceding state in S1 P is true. So, you can say that in S1 also P until R is true. Now, we look into state S2. So, it is going from in S2, if you say we are having a path from S2 to S3, S3 to S2 and S3 to S2 to S3, like that we are having this particular path. Along with that, when I am coming to S3, again it remain in your S3, S3 like that. So, these are the possible execution trace. Okay. Now, when we go for your S3, then from S2 I am getting these are the execution trace, from S3 we are getting these are the execution trace, because one is subset of other, or we can say that this is the subsequence of this particular path from S2. Now, what will be the truth values of your P A, P until Q? If you look, we are concerned about in all path P until R, this is the formula. Now, what is the truth values of this particular formula in state S2 and S3? If you look into it, you simply say that P is none where it is true in all this particular part. So, now what will be the truth values of your A, P until R in state S2 and S3? I will explain it after explaining some more things to you. We will see what will be the truth values of A, P until R in state S2 and S3. Just I am not saying anything whether it is true or false at that particular moment. I will come back to it. Similarly, that next formula again you see that I am talking about in all path in future are holes or not. Now, here I have slightly changed the labeling function. In S3 I am having only Q. Okay. So, we are talking about A, F, R. Now, again similarly if you say that this is the same model, slight difference. Now, if I come to this particular point A, F, R, then you will find that from S0 we are going for all execution path, and we will find that in some future state we are going to get R is true, because this is a part where R is true, this is another part where R is true. So, basically S0, S1, S3, S2. So, R is true over here, or S0, S1, then S2. So, R is true over here. So, we are getting two possible paths, and in future state R is true. Similarly, from S1 also it is a sub part of this particular part coming out from S0. So, again we are having that it is true over here. Now, what will happen in this particular case if I am going to look for S3? So, we are going to get the part from S3, it will remain in S3, remain in S3 like that, or maybe it will go from S3 to S2, S2 to S3 like that. So, if you go this particular part, you will find that in future R is not true. So, that means this particular formula A, F, R is not true in model M. In state S3, it does not model A, F, R, because we are getting one part where R is not true. Now, when we start from this particular state S2, then what will happen? From S2 we are going to S3, then we are going to S2, again S3 like that, or maybe it is having that it is from S2 we are going to S3, then it will remain in your S3. Okay. So, here you just see that in this particular part somewhere again we are coming back to S2 and R is true over here, but if you go this particular part S2 is not true. So, in this particular case what happens, I am not going to whether we can conclude that whether this A, F, R is true in S2 or not, because we are getting this particular part where in future we are not going to get any future state where R is true, but I am not going to say whether A, F, R is true at that particular state S2 or not. I will come back to you, like that previous example I have said that I am not going to say anything about the truth values of that particular formula in state S2. Similarly, for A, F, R I am not going to talk anything about now truth values of this particular formula in S2, but I will come back and see what will happen now. Now, in this particular case, now what will happen? Now, we are going to talk about the timing behavior of our system. Now, if you look into the timeline, basically we are having three particular tenses: past, present and future. So, if we are in a present state, then we can reason about what happened in the earlier stage of past, or we can try to reason about that what is going to happen in future. But now I am in the present state. Now, what will happen? Now, we are having three distinct things: past, present and future. But the way we are defining the semantics of CTL, it says that the future includes the present. That means, if you look into this particular timeline, if this is my present state, these are my past, and from present I am going for future, then what will happen? The way that we have defined the semantics of CTL, it says that the future includes the present. That means, the present states also included in the future behavior. This is because of defining the syntax, that we have defined the syntax. So, that means, we are having only two norms, one is past behavior and one is future behavior. In where future behavior, the present is included. Now, see why it happens. One simple example I am going to say that we are going to look into that EFQ, how we have defined this particular EFQ or EFSI. So, we are going to look for the transition S1 to S2 to S3, like that we are going to look for one transition part, and we are looking for one particular state S, and what we say that S equal to S1. That means, our state of concern is S, and we are saying that this is S equal to S1. That means, starting state of this particular part, and for at least one SI. Now, we are going to look for one SI where MSI models your phi. Now, we are going to look for one SI, but in this SI we are not excluding this particular one. So, I may varies from now 1, 2, 3 like that, all possible values can vary, because we are not excluding this particular one over here. So, what will happen? That we are getting M S1, if it models phi, then what will happen? As for this particular definition, M S also models this particular EF phi. So, according to this particular definition, M S1 also models EF phi. So, see, this is due to the definition of the semantics. So, if a particular formula holds in a state, we will say that EF phi holds in that particular state also. So, similarly, AF phi will also holds in that particular state if phi holds in that particular state. Okay. Because this is the way we have defined the semantics, because we have not excluded this particular S1 from this particular any SI. So, this is the way that we have defined. So, that is why that present state also includes in the future behavior. Now, see the another one, that E phi 1 until phi 2. Again, what happens? We said that we are going to take any execution trace S1, S2, S3, S4 like that, S5. Now, what we are saying that we are concerned about a particular state S, and we are saying that S is equal to S1, the starting state of this particular part. We are saying that S1, and what we are saying that phi E phi 1 until phi 2 will hold in this particular state S, provided we are going to get some SI which models your phi 2. Just say that here in this particular phi 2 models, and all j less than I, we should have M as j models phi 1. Okay. So, phi 1 must be true in all those particulars. Now, what is this particular j? You just say that j is all preceding states of this particular part. We are not excluding S1 from here. We are not saying that all j apart from S1 is true. So, in this particular case, what will happen? Oh, sorry, it is not over here, but we are going to talk about this particular I. When I am talking about I, we are not excluding 1 from this particular I also. So, I may be 1 also. So, I may be 1 also. So, in this particular case, what will happen in S1? If phi 2 holds at that particular state, then what will happen? you will find that as according to this particular definition of particular semantics, E phi 1 until phi 2 holds in this particular state S 1 also. So, see that. That means, if phi 2 holds in a particular state, we will say that E phi 1 until phi 2 holds over there. Similarly, A phi 1 until phi 2 holds in that particular state. So, this is because of the definition of this semantics. So, the semantics that we have defined over here says that the present state includes in the future behavior also. But if we want to exclude the present behavior from the future, then accordingly we have to define the semantics. Now, you just take it as a task or as a homework, and you just try to define the semantics of this CTL formula, where the future behavior is going to exclude the present behavior. Okay, just see, it is simple. The way I have explained over here, because here I equal to 1, we have not excluded it. So, what will happen if I equal to 1, then it says that in S 1, if phi 2 holds, then we will get that E phi 1 until phi 2 holds in S 1. Now, I have given you a task, what you have to do, try to define the semantics of CTL formula in such a way that the future behavior excludes the present scenario. Okay. So, how to define the future or semantics for the CTL formula? It is a simple task, you can do it. Now, in this particular lecture, we will going to see some questions. Okay, simple question I am going to consider. The first question I am saying that consider a set of your atomic proposition x, where we are having 3 atomic proposition p, q, r. Okay. So, this is a set of atomic proposition. Now, we are saying that what is the power set of x? Why you need it? Because the labeling function, we have seen that the states will be labeled by the member of the power set of our atomic proposition. So, this is very simple. Now, if x is your p, q, r, then power set of x will remain, how many elements we will have? I think you know it is very well that we are having 8 elements. So, one is yours the null set, then only p, only q, only r, or maybe p q, p r, or q r, and the complete set p q r. So, this is the power set of x 1, 2, 3, 4, 5, 6, 7, 8. So, these are the all possible combination, and we say that this is the power set of x. Now, when we look for any state, say if I am having a state transition, say S 0 to S 1, S 1 to S 2 like that, then if you say that this particular S 1 is labeled with say p and q. So, what does it means? That atomic proposition p and q is true in this particular state S 1, but r is not true. So, what is that p and q? It is a member of this particular power set. That means, the states will be labeled by the member of power set of our given atomic set. So, x is a set of atomic proposition p, q, r. So, these are the component of this power set, and the labeling function is going to pick up any member of this particular power set, because it says that these are the atomic proposition true in this particular one. So, if S 2, if say that it is not marked with or any atomic proposition, that means what says that we are going to take this particular member phi, it says that it is a null set, none of the atomic proposition is true in this particular set S 2. And if says that p, q, r is marked over here in S 0, it says that all these 3 atomic proposition is true over here. Okay, next question, what I am saying that show a Kipke structure such that in a particular state E x p or r holds, but E x p q and r does not hold. That means, what we are looking for, say there exists a part in next state either q or r holds, or I am saying that, but there exists a part in next state q and r is not true. So, this is very simple. Say I can say that this is the state S 0, since it is your next state, we have to look for one particular next state only. Okay. If I say that it is labeled with q and it is labeled with r, then what will happen? There exists a part in next set q or r holds. So, if you say that since q is true over here, what you can say that q or r is also true over here. So, we can say that at least we are getting one state. So, in S 0 there exists a part, in next state q or r is true. But if you look into this particular next state, it is q is true, but r is not true. In this particular state r is true, but q is not true. So, q and r is not true in any one of these particular states. So, that means, in this particular model in S 0 there exists a part, in next state q and r is not true. So, we are saying that show a Kipke structure such that in a particular state in all part in future q or r is true, but there exists a part in future q and r is not true. So, what we are saying that in all part in future q or r is true, but there exists a part in future q and r is not true. Now, just look for this particular model, say S 0. So, we are having three possible paths. Now, here if you see these particular things, then what will happen? We are having three execution traces from S 0. This is the first part, say pi 1, this is the second part pi 2, and say this is the third part pi 3. Now, if you follow this particular part, we are getting one state in future where q is true. So, I can say that q or r is true in this particular state. Similarly, in pi 2 also we are getting one state where r is true. So, in this particular state I can say that q or r is true over here. Similarly, in the third part pi 3 we are getting one state where r is true. I can say that q and r is also true over here. So, in all these three paths from S 0 I am having three possible paths. So, in three paths we have seen that we are getting one future state where q and r is true. So, we can say that in S 0 A f q or r is true. Now, look for the second formula that there exists a part in future q and r is true. If I am having this particular labeling, then you will find that none of this particular part in none of the states q and r is true. So, that means we are not getting any part where in future q and r will be true. So, that is why I said that this particular formula E f there exists a part in future q and r is false in this particular state S 0. Now, just look for another way of looking into the CTL formula. What I am saying that express the following property in CTL. Is it possible to get a state where started holds, but ready does not holds? So, if you look into this particular statement, what will happen from here we can capture two keywords. One is your started and another one is ready. That means, what we can say that these two are my atomic propositions. So, we can have some signals in my systems where the value of these signals may be either 0 or 1. If it is 0, we can say that it is true. If it is 1, if it is 1, we will say that it is true. If it is 0, we will say that it is false. So, these are the two signals we can think in my system. That means, we can map these two as my atomic proposition of my system. Now, we have to say that it is possible to get a state where started holds, but ready does not holds. That means, you can think something like that. We have designed a system and after that it is going for operation. Now, we have started a machines, but it is not going to the ready state. Okay. So, it is you have started it, but it is not going to the ready state. So, whether we have to reason about such type of property now, whether this property can be expressed in your CTL or not. So, is it possible to get a state where started holds, but ready does not hold? So, you will find that we can express this property in CTL something like that. There exists a part in future where the started is true, but ready is not true. So, this property we are going to capture in CTL like that. There exists a part in future started is true and ready is not true. So, this is the way we can capture it. Now, if we are having the model of the system, now we are going to look for the truth values of this particular formula, and we will see what are the states that formula is true and what are the states this formula is false. So, another property is, as you see that express the following property in CTL. The property says like that: for any state, if a request of some resource occurs, then it will eventually be acknowledged. Now, it says that if we are going to look for your distributed system or maybe concurrent system, what will happen? Same resources will be shared by different processes. So, what we are saying that if we are requesting for a particular resource, it may be a shared memory or it may be something else also, it may be some other devices also. If we are requesting from some resources, then it will eventually be acknowledged, because if say if I am going to access a shared memory, eventually I should get it, then only I can progress. If I cannot get it, then what will happen? I will go into the starvation. No, when we design a system, that system must satisfy such type of property. Now, this is we know the meaning of this particular property. Now, when we are going to formally verify it, somehow we have to capture it formally. Now, we are going to see whether this property can be captured in CTL or not. Now, again you shall see that here we are having two keyword, one is your request and second one is your acknowledge. That means, we can say that some process or some process might have raised a request, we said that this is a signal. If it has raised a request, then it will go to active high, and if it is not requesting it, then it is active low. So, request can be treated as your atomic proposition, its value is either true and false. When it is that resource is granted to the process, then what will happen? We can say that it has been acknowledged. Then again we can say that acknowledge is a signals, its value is either 0 or 1. So, here we can say that this is also an atomic proposition in my system or of my model. So, we are getting two atomic proposition, request and acknowledge. Now, with the help of these two signals, we will define this particular property in CTL. Now, what we can say that if somebody has requested from some resource set, it should implies that in all part in future it must get the acknowledgement, and this property should hold globally in the system. So, that is why I am saying that in all part globally, if it is requested, then it should say that it should get an acknowledgement wherever the system will go. So, that is why I am saying that in all part in future it should get the acknowledged. Okay. So, in all part globally it must be true. So, if in a particular state if requested happen, then from that particular state wherever you go in all part in future we should get the acknowledgement. If there is some paths where we are not getting the acknowledgement, then what will happen? If I follow that particular path, that system is going to get starvation, because it is not going to get the resources. Now, this is the way that we have to look for the properties of our system, and we have to express in your CTL, and we are going to look for the truth values of those particular CTL formulas in our system, say whether this is true or not. Okay. So, this is about our one particular class of logic, temporal logic called CTL, computational tree logic. We have seen how to define what is the syntax of your CTL, how to define it, and what is the meanings. We have seen the semantics of those particular CTL formulas, and secondly, we have seen how to define the semantics, it is with respect to a model, and secondly, we have seen that the CTL formulas are basically state formulas. The truth values defines over a state of a model. Okay. So, with this I am I will stop here today. In next class, we are going to see some of the notable equivalents of our CTL formula, which will help us for verifying our system. Okay. Thank you.